Continuing with the equivalent circuit diagram of the transformer, today we will discuss the equivalent circuit diagram referred to the secondary side. Before going into the equivalent circuit referred to the secondary side, in the last session you are unable to derive the equation for the voltage equation for transformer or approximate equivalent circuit diagram referred to the primary side. It is incomplete, just I have to finish it off. Then we will move to the equivalent circuit diagram of the transformer referred to the secondary side. You are already aware of this vector diagram, that is V2 by K is the voltage and the I1 is the current which is lagging 5, adding I01 R01 which is parallel to I1 and I1 X01 which is perpendicular to I1, then what I am getting is V1, that is it is referred to the primary side. Then it is I1 Z01. Then step by step I am trying once again the same vector diagram with at individual steps I am resolving I1 RON and I1 X1 to its X and Y components. Okay, here I got I1 R1 which is lagging I1, I1 R01 is in phase with I1. Now I am resolving along X and Y axis the component of this. Therefore I am representing this as AB, this as point C. Then I am resolving this as a Y component, that is CD, and the BD is the X component of I1 R1. That in the last class we are seeing, we are taking the triangle BDC. Once you have to apply cos phi, another one you have to apply sin phi, so that you are getting BD and CD, that you are seeing here. That is BD is I1 R1 cos phi you are getting, and similarly you are getting BC is equal to I1 R1 sin phi, this vector. Then to this BC I am adding I1 X01 which is perpendicular to current I1. Once again I am resolving this into its X and Y component. Therefore I am resolving this. Then this angle is become phi, because this is phi. This angle is 90, this 95, 90 plus 90 minus 5, then this is also 90. Just you have to look into the diagram. Just I am resolving that. Okay, just you can see here. You can see this particular triangle. What is that? This particular triangle. This, if you are taking this is 5, 90. This is 90. This 90 minus 5. Ultimately, this is 5. Okay, it is 90 plus 90 and it is 90 minus 5. It is 90 minus 5. It is 90. Therefore, this is value is 5. Okay. Now, if you are adding I01 and I01, what I am getting is V. Okay. That is, I am calling this as CF. Then, once again, you are finding out CG and FC from the triangle CGF. Once you have to apply X sine function and another time you have to apply the cos function. So that what I am getting here is, that is FG, that is Y component is I1 X1 cos phi, and the X component what I am getting CG is I1 X1 sin phi. These are the X and Y component of I1 X1 I am getting. Means I am resolving I1 R1 and I1 X1 to its X and Y component, so that I want the total value of the V1, that is V1. Now mathematically, just I want this AF, then from the right angle triangle of AHF I am finding out AF square is equal to AH square plus HF square. The same thing I am writing here, that is for I am considering this is for a lagging power factor AHF. I am taking AHF, then we are deriving the equation here. That is AF square is equal to what is the total EF? EF is AB plus BD plus DH, AB plus BD plus DH plus the square whole square, this whole square plus FH square, that is nothing but FG minus GH, okay, or HG. It is FG minus HG, okay, whole square. However, you can see here that is GH or HG is nothing but the DC, that is a DC, that is were calculated here, I1 R1 sin phi, okay, that you have to do it. And the DH is nothing but CG, that CG is nothing but I1 X1 sin. Just you have to merely substitute these values in this equation. Then what I am getting here is V2 by K plus I1 R01, that is AB is V2 by K, and BD is already it is X component of I1 R1, that is I1 R1 cos phi, and plus DH, the DH is nothing but CG, CG is I1 X1 sin phi whole square. Then FG, that is FG we know, that is I1 X1 sin phi. So this is I1 X1 cos phi, that is FG, and HG you have to deduct, that is I1 R1 sin phi whole square. Okay, this is how we have to calculate V1 square. Ultimately, if you are simplifying this equation, what I am getting here is V1 is equal to V2 by K plus I1 R1 cos phi plus I1 X1 sin phi. This is the equation what you are getting for the voltage and directly. These are all drops are taken. You have to add algebraically here because you are resolved and using the Pythagoras theorem you are finding out this voltage. Otherwise, you have to make use of the previous one, that is straight away, that is there is no necessity of, there is no necessity of the deriving this particular equation. You can take directly in the polar form that we have discussed in the last class. Okay. Then for unity power factor, this in this equation, if you are putting phi is equal to 0, then it is becomes 1. Then sin 0 is 0. Therefore, this is 0. Therefore, what you are getting is V2 by K plus I1 R1. For the leading power factor, put phi is equal to phi as a negative. Here cos of minus phi is cos phi only, therefore I1 cos phi you are getting here. But sin of minus phi is minus sin phi, therefore it is minus I1 X1 sin phi. This is how we have to derive the equation for the voltage V1 in terms of V2 by K. Then we will move to the equivalent circuit diagram of the secondary side. We know this is the circuit representation of the transformer with R1 X1, R2 X2. It is a normal transformer and no load component of R0 and X1. Then you have to draw the circuit, means what I am doing here, R1 and X1 I am transferring to the secondary side. It is referred to the secondary side, means R1 and X1 you are bringing to the secondary side. Similarly, R0 and X0 also you have to bring to the secondary side. Therefore, to bringing the terms from primary to secondary, what you have to do? For resistance and reactance, you have to multiply square of the transformation ratio. Square of the transformation ratio means R1 in the primary is equivalent to K square times R1 in the secondary. You are transferring from here to here. Similarly, X1 in the primary is equivalent to K square times X1 in the secondary side. Similarly, R0 is also in the similar fashion of transfer, that is R0 in the primary is equal to K square times R0 in the secondary. Similarly, X0 in the primary is equivalent to, it is a K square, K square is merging here, it is K square times XO1, K square times XO1. This is how we have to transfer these parameters to the second side. Similarly, I1 you have to transfer to the secondary side, then what you are getting, just I am putting here, it is I1 by I2 is equal to K, what we need is I2. Therefore, I2 is equal to I1 by K. Therefore, here if we are transferring I1 to the secondary side, it is become I1 by K. It is become I1 by K. Here it is a V1. I want to transfer to the secondary side. Once again, I apply V2 by V1 is equal to K. What I am interested is V2. V2 is equal to nothing but it is a K times V1. It is K times V1. Therefore, I am writing here it is K times V1. This is how we are transferring R1 X1, R0 X0, I1 and V1 to the second side. This is the circuit diagram which is referred to the second side. Merely by multiplying the K square to the resistance and reactances, K to the voltage and divide by K to the current. That is I1 is become I1 by K, whereas voltage is become V1 is equal to K times V1. Okay, this is and the second is intact as it is R2 and X2. Here it is V2 because we are transferring this to secondary side. Okay, further we'll make this is once again what I am getting in the last the diagram, that is this diagram. Now I am saying a diagram I draw. Then we are making the assumption that the current I0 dash, that is actually it is I0 dash by K. I0 dash by K actually. This can be transferred to this, it does not make much difference. Therefore, the simplified version of the diagram, what I am doing here is, I am shifting it to here. Therefore, the total current what I am getting, even K square R1 and K square times X1, now it is become I2 because this you are transferring to this side. Here now it is a I1 by K. It is the current is I1 by K. The voltage is K times X1. Okay, it is K square times R1, K square times X1. Then this is shifted here. Then R1 and X1 is as it is. The load is as it is the same. Now we have to draw the equivalent circuit diagram. Once again, I am taking the diagram of it is K times R2 and it is actually K square is marked here. K square times X0 is I1 by K. K square R1, K square X1, R2, X2 and V2 here. Therefore, what I am getting here is, once again, you can add these two resistances and two reactance and you will replace by single resistance and single reactance and the load. That is, here it is now the transfer to the second side. Now I am defining R1 or R02, that is equivalent resistance of the transformer referred to the secondary. Therefore, it is K square times R1 plus R2. Here XO2 is K square times X1 plus X2. It is equivalent reactance referred to the secondary side. It is equivalent resistance referred to the secondary side. Now, the voltage is K times V1 and it is I1 by K. It is I2. Then the voltage here is the V2. This is how we have to draw the circuit referred to the secondary side. The simplified version means this particular element is neglected for approximate equivalent circuit. Therefore, it is K times Vn and V2 and equivalent resistance is RO2, equivalent reactance is XO2. This is how we have to draw the approximate equivalent circuit of the transformer referred to the secondary side. For this, you have to draw the vector diagram. Just I am drawing the vector diagram here. This is RO2, XO2, K times V1. Here it is a V2. Start with the V2. Then the current here is I2. Means V2, I2 you have to take as a reference. V2 as a reference. And depending upon the current I2, lag or lead or a unity power factor. Starting with the lagging power factor, I am drawing here the vector diagram. V2. I2 lags V2 by angle of 5. Then add I2 R2 which is parallel to I2. Then add I2 X2 perpendicular to I2. Then the total value what you are getting K times V1 because from V2 to you will get K times V1. Therefore, this is I2 Z02. This impedance triangle. This is the impedance triangle. This is impedance triangle. Okay. Therefore, in the equation form, how we are getting the KV1, that is to add add to the V2, factorial add V2 plus I2 into bracket RO2 plus JXO2, RO2 plus JXO2, or it is V2 plus directly I1 Z02, I2 plus I2 into Z02, V2 plus I2 Z02. That is this plus this vector, that also gives the K times V1. Okay, for different power factors that you can write here, K V2 is taken as a reference, therefore write as V2 an angle of 0 degree. Then I2 we know the with the power factor lag or lead or anything power factor. Here I am considering for lagging, therefore I am taking it as minus 5. Therefore, what I am getting is KV1 is equal to V2 an angle of 0 plus I2 an angle of 5 into R2 plus 3XO2. Similarly, we can try for the unity power factor. For unity power factor, V2 is equal to V2 an angle of 0, that is a reference, whereas cos phi is 0, therefore it is, sorry, phi is 0, therefore I2 is an angle of 0. Just you have to substitute the values here. What I am getting is V2 an angle of 0 plus I2 an angle of 0 means both voltage currents are in phase into RO2 plus say X2. Similarly, we can write for the leading power factor. Here, phi you have to take as a negative, positive value. Here, phi you have to take as a positive value. Then you can write here, that is V2 an angle of 0 degree plus I2 an angle of 5 into RO2 plus say X2. This is how you have to write the equation for the voltages. Once again, to derive the equation, same procedure you have to follow here. Here V2 is a reference and I2 RO2, I2 XO2 and K times V1. Okay, that is I2 ZO2. Sorry, it is I2 ZO2. Yes, I2 ZO2. Then once again, I am resolving I2 RO2 into two components. It's X and Y component, X and Y component, and finding out that is a DC and BD as did in the last for refer to the primary side. Okay. Similarly, I2XO2 is also resolved into two component. Then the finally you are finding out the value of FG as well as you are finding out the value of CG. Then ultimately you are getting the value of KV1. Then use the equation triangles. Once again you have to apply the Pythagoras theorem. In here you are getting KV1 is V2 I2 RO2 cos phi plus I2 XO2 sin phi. Okay, after simplification, just it is a Pythagoras theorem and substitute the values and find out the KV1. Then for the different power factor, for leading power factor, you have to take phi as a negative, and for unity power factor phi is equal to 0. Therefore, what you are getting is V2 I2 RO2 because cos phi is 1 whereas sin phi is 0, then you are getting this. Then similarly for leading power factor, you have to put phi as a negative value and find out the expression, that is V2 I2 RO2 cos phi, because cos of minus phi is cos phi and minus of phi is minus sin phi, therefore it is I2 XO2 sin phi. This is how you have to calculate the voltages when if you are referring to the secondary side.